What if you could hold 800,000 years of Earth's history right in your hands? I'm not talking about a history written in some old, dusty book. Nope. This one's frozen solid, deep inside the ice sheets of Antarctica. Today, we're going to put on our detective hats and figure out how to read this incredible frozen archive. So, let's get into it. Seriously, think about that for a second. How on earth can we possibly know what was in the air 800,000 years ago? I mean, that's way before humans were even a thing. It sounds kind of impossible, right? Well, that's the big mystery we're going to solve today. And the answer, it turns out, is locked away in one of the most remote, frozen places on the entire planet. All right, so here's our game plan for this journey. We'll kick things off with these frozen time capsules. Then we'll get into decoding the ice itself and reading the ancient air trapped inside. After that, we'll see how scientists build an 800,000-year-long clock, what this whole story actually reveals, and finally, we'll wrap up with the scientists' fine print, the important details. Okay, first up, let's talk about our main piece of evidence. These really are Earth's very own frozen time capsules. So what exactly is an ice core? Well, imagine scientists drilling way, way down into the massive ice sheets in places like Antarctica or Greenland. They pull out these long, perfect cylinders of ice. And here's the cool part. Every single year, a new layer of snow falls, burying and squishing the layers from the years before. Over thousands and thousands of years, all that snow gets compressed into solid ice, creating this amazing, perfectly preserved, layered archive of the past. And this is what absolutely blows my mind, the sheer amount of stuff we can learn from just one of these cores. You've got these tiny little air bubbles trapped inside, which are literally samples of ancient air. That's how we can measure things like CO2 and methane from way back when. The ice itself, that tells us the temperature. And you even get these layers of ash and dust that act like little bookmarks in time, telling us about huge volcanic eruptions, or even how wind patterns used to be. Okay, so first big question. How in the world do you turn a piece of ice into a thermometer? I mean, really? Well, the secret is all in the chemistry, right down at the atomic level. So let me introduce you to our two main characters in this story, oxygen-16 and oxygen-18. Now, they're both oxygen, right? But oxygen-18 has a couple of extra neutrons, which just makes it a little bit heavier. And this tiny, tiny difference in weight, that's the whole secret. See, the lighter oxygen-16, it evaporates from the ocean more easily. But the heavier oxygen-18, it's kind of lazy. It prefers to condense and fall back down as rain or snow sooner. Okay, so here's the really crucial part. As all that water vapor travels from the warm oceans towards the poles, the heavy oxygen-18 tends to rain out first. It just can't make the whole trip. And when the planet is colder, this effect is even stronger. So what does that mean? It means the snow that falls on Antarctica during a really cold ice age is going to have way less of that heavy oxygen-18 compared to snow that falls during a nice warm period. So by measuring that ratio, how much heavy versus light oxygen there is, scientists can build this amazing proxy for temperature that goes back for ages. All right, so we've got the temperature figured out. That's amazing. But what about the air itself? Well, for that, we need to look at those tiny bubbles trapped inside the ice. And honestly, this is what makes ice cores completely irreplaceable. They're not just some clue or a proxy. They are actual physical samples of Earth's past atmosphere. These little bubbles are like tiny time capsules, perfectly preserving the air from hundreds of thousands of years ago, just waiting for us to come along and analyze them. But, okay, here's a super important scientific detail that you have to get right. The air and the bubbles and the ice around it, they're not the exact same age. Think about it. Snow falls and it slowly gets buried year after year. For a long time, we're talking decades, even centuries, air can still move around in that packed snow layer, which is called firn. It's not until it's buried really deep, maybe 50 to 100 meters down, that the bubbles finally get sealed off for good. So the air inside is always a bit younger than the ice right next to it. And that's something scientists have to carefully calculate. All right, so we have the temperature and we have the air samples, but how do we know how old they are? Building a reliable clock that stretches back 800,000 years is, you guessed it, one of the biggest challenges in this whole field. See, the big problem is that ice doesn't just stack up neatly like a layer cake. The sheer weight from all the ice above makes the deep layers at the bottom flow outwards. I love this quote from MIT's David McGee. He says to think of it less like a cake and more like pancake batter spreading on a griddle. The deeper you go, the more those layers get stretched and thinned out. So you can't just count them like tree rings. It's way more complicated than that.
So, to solve this, scientists bring out a whole toolkit of different methods. Yeah, for the top part of the core, the more recent ice, they can just count the annual layers. But as they go deeper, they have to get more creative. They'll look for layers of volcanic ash from eruptions we know the date of. Those are like perfect time-stamped bookmarks. They use really complex computer models to calculate how the ice flows and stretches. And they can even line up different ice cores from different places by matching the unique up and down patterns of gases like methane.
Now, it's really important to remember that this isn't perfect. The deeper you go, the more those layers are squished together, and the bigger the uncertainty about the exact age gets. Near the surface, you might be able to tell the difference between one year and the next, but way down at the bottom, a single centimeter of ice could represent an entire century or even more. So, after all of that incredible scientific detective work, what's the payoff? What's the story that 800,000 years of ice is trying to tell us? Well, it turns out it reveals a fundamental, deep rhythm to our planet's climate. What the ice cores show, clear as day, is that our planet has a natural pulse. For at least the last 800,000 years, Earth has cycled back and forth between long, cold glacial periods, ice ages, and these shorter, warmer periods in between, called interglacials. And that's exactly where we are right now. But it's not just about this rhythm of warm and cold. The ice cores revealed something else, something absolutely profound hidden inside that cycle. A connection between two key players that honestly changed our entire understanding of how Earth's climate works. When you take the temperature data from the ice and you plot it right next to the carbon dioxide data from those little air bubbles, you get this, an unbelievably tight connection. They move in perfect lockstep. When CO2 goes down, the temperature goes down. When CO2 goes up, the temperature goes up. For 800,000 years, these two have been doing this perfect natural dance together. Now look, great science is always honest about its limits, right? So it's only fair that we look at the fine print. Let's talk about the known complexities and challenges that scientists are always working on. The main thing to take away from this is that scientists know all about these issues. They aren't surprises. They actively account for the ice getting squished, for gases moving around in that firn layer, even for how wind might mess with the snow on top. For every single one of these challenges, they have a strategy to deal with it. Whether it's using powerful computer models or cross-checking with other ice cores, it's all about making sure that the final story the ice tells is as accurate and reliable as humanly possible. So in the end, that's what this is all about. The ice core record gives us the rulebook. It shows us our planet's natural rhythm. It lays out in stunning detail just how deeply connected temperature and CO2 really are. And it gives us the ultimate measuring stick to see just how far outside of that natural rhythm we are today. The story of the past provides the essential context for the new chapter we're writing right now.